So now we're looking at section 17.7. And in 17.6, we found a way that we could determine whether or not a reaction is spontaneous by calculating the total entropy change for the universe. And obviously, this is not something what you want to do or have to do every single time we wanted to determine whether or not a reaction is spontaneous. And so there's a more convenient approach that we can use to determine whether a reaction will be spontaneous in the forward or the reverse direction. And that is using this state function known as the Gibbs free energy. And so the Gibbs free energy is written as G equals H minus Ts, where H is our enthalpy, S is our entropy. And one definition of it is it's the maximum amount of work that can be extracted from a chemical reaction. This is really sort of where it gets this name of free energy. And we can look at the Gibbs free energy change then by looking at the deltas in the H and in the S, and this will give us a delta G. And because this is a state function, we can figure out the change by looking at the final state minus the initial state. And this is also really useful because it's using the same sort of approach as we did for determining the spontaneity of the system by looking at the total change in the entropy of the universe. And so here's our expression delta G equals delta H minus T delta S. And we have the following criteria for spontaneity. We see that if delta G is less than 0, we have a spontaneous reaction. If delta G is greater than 0, we have a non-spontaneous reaction. And if delta G is equal to 0, that means that we have a system that is at equilibrium. And so we can see how do these different terms affect spontaneity. This is the enthalpy for the reaction. This is delta S for the reaction. And again, the usefulness of this function is that we're considering only properties of the system itself. We don't have to look at what's happening in the surroundings. And so we could rewrite this really as showing that these are referring to the particular reaction that we're interested in this particular system. And we can also see then how the enthalpy and the entropy contribute to spontaneity. And so, for example, if I want my delta G to be negative, I want my delta H to give me a negative number, and I want this term to give me a negative number. And so if we put that together, we can see that delta H less than 0 and delta S greater than 0 will tend to favor spontaneity. Because if delta S is greater than 0 in my system, I'm creating disorder in my system that will make this entire term more negative. And the more negative this term, the more likely it is that delta G will also be negative and therefore spontaneous. Likewise, the more negative delta H is, the more likely delta G is going to be negative. And so an exothermic reaction will tend to contribute toward spontaneity. And I think this makes sense too, looking at our previous example. If we consider what's happening in the surroundings, if I release heat to the surroundings, I'm increasing this entropy of the surroundings as well. But here we can use these using only properties of the system itself to determine whether or not this reaction is spontaneous. So delta H minus less than 0 and delta S greater than 0 will favor spontaneity. Likewise, if we have delta H greater than 0 and delta S less than 0, this would tend to favor non-spontaneity. In other words, the reverse reaction would be spontaneous. And we can set this up together in a grid. If we look at what delta H is doing and what delta S is doing, mathematically, what will our values of delta G be in each of these scenarios? Well, if delta H is negative and delta S is positive, this equation will always give me a negative delta G. So delta G will always be less than 0. So if I have this combination of terms, my reaction is always spontaneous. Likewise, if I have an endothermic reaction and a decrease in entropy inside the system, my delta G value will always be positive. And this reaction will never be spontaneous. We could say the reverse reaction will always be spontaneous. But what about these mixed cases if they're both positive or both negative? Well, in those cases, spontaneity depends on the temperature, because the relative contributions of this enthalpy and this entropy will change depending on the temperature at which this reaction occurs. And so what we'll find here is that delta G will be less than 0 at high temperature. It'll be spontaneous at high T. And delta G here will be less than 0 at low temperature. And this is a table that's repeated in your book, and it's also posted in the slides if you want to see the relationship between these different terms. Now we can look at a particular example of this to illustrate this temperature dependence of spontaneity. So again, we can write delta G is equal to delta H minus T delta S. This is our expression for the Gibbs energy. And we can go back to this familiar reaction, this familiar process of ice melting. So if we go from H2O solid to H2O liquid. So if we think about the forward reaction, ice melting, we find here that if we want to melt ice, we have to give this system heat. And so this is an endothermic process. And in this process, we go from a solid crystalline phase to a liquid phase. And so delta S is also positive for the forward reaction. So how do I know whether it's spontaneous? Well, if we look at how these terms will enter into this expression, we see that delta H is positive, and that doesn't help us out. But delta S is positive, and so if I want to make this term more and more negative, in other words, if I want to promote spontaneity, a way that I can do that is by cranking up the temperature here. Because the higher the temperature here, the more negative this part of the expression becomes. And really, that's just a long-winded way of saying that spontaneity will be favored at high temperature. So delta G less than 0 at high temperatures, which is just a long-winded way of saying that ice melts spontaneously at high temperatures. And I like using this example because I think this is very intuitive to us, how water behaves. But why does water melt at high temperatures? Because at high temperatures, that's when delta G becomes less than 0. That's when this process in the forward direction becomes spontaneous. Now, likewise, we could just look at that reverse reaction. What happens if we start out with liquid water and we freeze it? Well, for the forward reaction here, our delta H has to be less than 0 because we need to lose heat to go from liquid to ice. And we are going to a to a more well-ordered system, less disordered, since we're going from a liquid to a crystalline solid. And so our delta S is also negative. And what we'll find here is delta H is helping us out. That's helping our delta G become negative. But delta S is working against us here because that will tend to make this term positive. And so we want our temperatures to be low. And so what we'll find here is that delta G will be less than 0 at low temperatures, which again is just a long-winded way of saying that water freezes spontaneously at low temperature. So why does ice melt and freeze at 0 degrees Celsius? Because that's the temperature at which this sign changes over from positive to negative if we're looking at this reaction, or from positive to negative if we're looking at this reaction in the other direction.